Okay, let's get started. So far we've dealt with TCP, we've dealt with select to do TCP for multiple clients. Today we'll do, well, maybe we'll just review briefly the whole session idea for TCP, and then we'll look at UDP as well, which is something I wouldn't recommend using most of the time, and maybe we'll see why today. But it's still good to know sort of what's available and how it all fits together. And then maybe we'll get around to multi-threading, or at least multi-process dealings with other clients as well. So let's see. Okay, starting out with TCP, we have two endpoints. All right, so here I'm just briefly review what's going on. Right, so we have let's see, it's not a sender and a receiver. We can call it a client and a server if you want. Client and a server, but of course there's no real difference except that a server is one that listens to a port, right, and then eventually receives these incoming connections. And then we have a network in between. I'll find my cloud again, and we establish somehow a session that goes through the cloud to the server, and it's a bi-directional link. We call it, well, shouldn't really call it a link, but it's a TCP session. Right, so on these two ends we have the client address and then also the client port. So we can call that, just client port. And on the other end we have the server's address and the server port. Okay, so these four pieces together uniquely identify a TCP session. There cannot be two ongoing TCP sessions with the same pair, or same quartet, I suppose, of these, with the same pair of tuples, pair of pairs. So this is sort of fixed. For a given client, you only have the one IP address. For a given server, you probably only have one IP address there as well. And then the server port is probably fixed as well. Right? You probably, any given server listens only to one port. Port 80, port 25 are the ones we used so far. So if you want to have multiple connections from this client, you can imagine for a web browser now. A web browser might want to have multiple connections to a web server because it has a few different ongoing communication sessions. Right? It might be convenient to have multiple connections. In order to get that to work, all we have to play with then is this port. Right? We can change the port. We can start a new connection, come up with a new port, connect to the other end again. So now we have two unique TCP sessions. Why do we need a unique identifier like this, do you think? Why do we even care?
We don't want other people, other servers with other ports to kind of get the message.
Okay, so one theory is we don't want the network to get confused and send our messages to the wrong server. So that's good, but it's actually enough to have just an IP address for that. The network doesn't know about TCP. It doesn't know about ports. It never looks at those things, except for some weird firewalls and things that really shouldn't be there. Okay, so by design, at least, the network doesn't know about ports. So it has something to do with the end hosts. So the thing is, when the server receives a packet, it has these four pieces of information in it. The server now needs to know not only which application to deliver to, but it needs to know which file descriptor. Right? The server, a web server, might have 100 different file descriptors open, all talking to different clients. In comes a new packet. It comes to the server's IP address, obviously. Okay, it comes to the same port, so it can't do anything there. It comes from the same client IP address, maybe. It's not clear. So you might have several clients, you have different IP addresses, but say one client now establishes two connections. Makes one socket connect, another socket connect. Right? In that case, you don't want to confuse which incoming packet goes on which file descriptor. In order to get that resolved, you have to have all these 4 pieces. Okay, so now when a packet goes in this direction, and this might be handy when you're looking at your Wireshark output or something like this. When it goes in that direction, the client, we have a source IP equals the client IP. Source port equals client port, right? But then when it goes in the other direction, it'll be the server's IP address that's the source. So this should be relatively obvious, right? But it's always turning these things around. So it's not like there's a server port and a client port that doesn't exist in TCP. There's only peers. And as I mentioned before, briefly, you don't actually have to have a server socket to establish a connection. If both endpoints know which port they want to talk to and when, they can just start it, and standards compliant TCP implementation should actually establish a session without the server port. But that seems terribly complicated and stupid. Right? So let's not go there unless you really want to make some weird hack. Okay. So all of this, in order to make this work, there's quite a bit of overhead. There's session establishment, right, which is a SYN packet, a SYN ACK packet, and an ACK packet. It's not so important, but there's actually 3 messages being exchanged just to get the session up and going. Then you send your data transmission, plus ACK. So you send the packet right from here. It includes a sequence number, just in case things get reordered along the way. So you send the packet, gets over to the other end, the server sends the packet back saying, okay, I got it. And then, so that can happen any number of times. N times this, and then we'll have session shutdown, which is another 3 messages. Okay, so this provides very nice ordered communication. It's reliable because of the ACKs. Everything's great, and you have this nice session. Things are divided into sessions, so you know you have separate file descriptors for everything. It's very convenient. It feels like just reading from a file. But what if we would just want to send a single message? I want to tell someone, hey, wake up, right? So now we got, I have a single message saying wake up. Now I got 1, 2, 3, 4, 5, 6, 7, 8 packets that need to go get exchanged. And well, not only that, so there's some cost involved, right? With all those packets are going to be in some minimum size. They're going to use a lot of data. If you're doing it on a mobile app, let's say, yeah, I suppose mobile is where it's most relevant, the amount of data you're using. And there's also some latency here. So say you want to send a message right away, and then you want to send another message at a certain time. Now you got to establish another session. Any one of these 7 packets could get lost. And if any one of those packets gets lost, then everything gets delayed, because now you're going to wait and you're going to see, okay, maybe I should retransmit and see if it, yeah. So you get lots of delays. It's hard to get good latency with this sort of setup. What you could do, of course, is you could just, okay, let's back up. All right, we want to send a single message. This is kind of wasteful. If you want to send something with low latency, this is a bit of a problem because you have this long session establishment going on first, several round trips, which can be a problem. If you're talking to Australia, it's 200 milliseconds, or not quite, but close to 200 milliseconds. Add it all up, we're talking well over a second to just get this one message across. Okay, so another alternative might be to say, okay, why don't we establish a session proactively? Because we know I just want to talk to this one server. And then whenever I need to transmit something, I just transmit on that file descriptor. Right? So now we're done with the session establishment. That's just going to sit there forever. Eventually, when I have a message to send, I do this thing. Right? Message goes across, get the ACK back. So that seems pretty good. Because now there's no latency. The server gets the message right away, as fast as it would with UDP. There's really no difference at all there. Can you think of a reason why we would not want to do it this way anyway?
say there's 100,000 people that want to do the exact same thing, then the server has to keep track of all of them.
Ah. Okay, so that's a good point. So you have a very large number of potential message senders, but they don't usually send anything. So now, with this system, you would have 100,000, in this example, 100,000 established sessions. We're sending 300,000 messages, and then in the end, turns out there was only one of them that's ever going to send a message, right? So now we're sending 301 messages, and then we're 300,001 messages. And then one message goes off, and eventually they shut down another 300,000 messages to get actually one piece of information across that. Okay, that's a good example. I was thinking of something different.
I assume you have a limit to the amount of ports you have?
Yes, there is a limit to the number of ports. It doesn't matter so much. So yeah, maybe we should discuss that too. So on the server side, it only ever uses one port. Right? So there's a limitation. On the client side, it's a 16-bit port. So how many is that? 1024 in 16 bits. Ay, ay, ay. That's 2 to the power of 10 is 1024. Okay, anyone else? 35,000? Oh, we're getting closer.
Something around 50,000.
65,536.
5,000.
All right.
It's the last time I'm not going to know my powers of 2.
Yeah, I guess so. But the problem is, I can't actually put it on a written exam because then you'll just spend all your time multiplying and stuff. Right? How do you examine this sort of thing? You can't do it. Anyway, you guys should know this stuff. Okay, 65,000 ports. So any given client can have 65,000 connections to the same server. Right? If it's to a different server, it doesn't matter because it's identified by all these 4 pieces. So any packet that comes into the server, well, it needs to be a unique IP address port pair. When something comes back, it's always coming from the same address and port over here. So on the recipient end, it's always coming on the same IP address as well, but there it needs to look at the port. So yeah, basically, as long as you stay under 65,000 connections per client, you should be good. In the case where there's a NAT box, a network address translation, that doesn't actually work out, and that's a CS450 topic. Let's cut it off there. Okay, so no, I don't think that the port number limitation is a concern here. Okay, so we had wastefulness with lots of connections that we maybe didn't want. Good point. And then, well, there's some other reason. A lot of things actually use UDP. Have you heard of something in particular that uses UDP instead of TCP for performance?
Voice over IP and streaming.
Ah, voice over IP is a good example. Streaming video, yeah, sometimes they do it, sometimes they don't. For real-time streaming, they do it. Okay, so why would it be important for voice over IP? Let's talk about voice over IP. It usually sends 64-byte packets. Right? So there's very short, I don't know actually how long it's for, but they send something on the order of 100 packets per second, and they're 64 bytes each, something like that. Okay? So, and it's very important that that packet gets there on time. If you think about on the phone, well, maybe you've never done this, but there isn't really many voice connections on regular phone now that have long latency. But with Skype, I'm sure you've noticed. Right? Sometimes it gets really annoying. The telecommunications union something, they say 200 milliseconds is the limit. And if you go over 200 milliseconds of latency in a voice call, then it's not usable. Right? And the reason is, it's hard to tell if they if the counterpart is saying something or not. There's always weird effects. Okay, anyway, so we need to have low latency if we want to do voice over IP. Same is true for real-time video streaming. There's some football game, and you need to see when the goal happens, not a few seconds later. Okay? Other examples is gaming. So you write a computer game and you shoot, right? You want to make sure that shot gets away right now, not later, because it might matter a lot to gameplay. Okay, so none of that seems very relevant here, right? Because we're saying we're sending the data right away. We have our session established, and as soon as some data comes, we send it. So what's the big deal? I mean, why not do that with TCP? It's a tricky one. Yeah. So TCP guarantees order, delivery order of the packets. And it guarantees that every packet makes it. The combination of those two is difficult when it comes to latency. So now say one packet, you have 100 packets to send, the first packet gets lost. Right? All the other packets make it. Now on the server, we have sender here now and receiver at the other end. So this sender sends 100 packets, the first packet gets lost, the server gets everything else. Now what's it supposed to do? It can't deliver anything to the application because it needs to go with the first one first. So now, actually what TCP does is say, well, I'm still waiting. As soon as it gets number 2, it doesn't say, yeah, I got number 2. It says, well, I'm still waiting on number 1. Right? So now it's sending back 99 packets saying, yeah, I'm still waiting for number 1. Right? They all come back, and now the client gets to send another packet, and hopefully that one makes it. Right? And then eventually the server can deliver everything. So, well, if you need that guaranteed delivery and ordering, there isn't much else you can do. You're gonna have to wait for that packet to come across. There's some neat coding tricks you can pull. Maybe we'll cover that in 450 as well. That sort of adds some redundancy, but in general, for whatever TCP does now, cannot be done. So why is it that, well, so in these other applications, somehow we're okay with things being out of order and lossy. Right? If we were not, if you're downloading a file, it's certainly not okay. You got to get, well, maybe out of order is okay, because you can reorder it later. But lossy is certainly not okay. Right? So for a download of a file, it's got to be perfect, it's got to be exact. For a voice over IP connection, perfect doesn't matter so much. It's really important that you get there before 200 milliseconds. If you lose a packet or so, what does that sound like? It's a little glitch or something, it's just a little silence. It's okay, we deal with it. Right? So if your application really cares about latency and doesn't care so much about reliability, that's when you want to use UDP. Okay? That's the only case, really. Yeah.
Does MP3 encoding already use 1C encoding to pinpoint?
MP3? Yeah, so MP3 is not a streaming format.
Because it's already sound, you can already expect something.
Yeah, so MP3 is lossy in a different sense. There's a loss of accuracy. Right? So what might be started out as a very sharp amplitude peak might get a little rounded off at the top. Things like that could happen, right? In this case, we're actually losing whole chunks of data in the middle. And if it's a video, it'll be like a weird move like that, right? Or something. And then everything just works. So, okay, so if your applications really care about the latency, oh, and maybe this is an even better criteria. If a packet that arrives late is completely useless to you, that's when you want to use UDP, because you're never going to get those late packets. It's just it'll never try again. It won't do anything for you. Okay, so let's talk about UDP then. I'll just pull up a header first, just so we see the difference. Maybe we can get both in one. That'd be nice. Is that it? That looks... No, that's IP and... Oh! No, this is UDP. Okay, anyway. So, here's what the whole... Forget the T... It says TCP here, that's not TCP. It's probably coming from a page that has both. So, here's what it looks like. That's IP. So basically your source address, destination address, those are the relevant things, the rest we can ignore for now. And then below that, so this is address 0 in the packet from some point of view. Right? When it arrives at the operating system and the network card has already removed its link layer header, then it looks like this. Before that, it might be a link layer header here. There might be some PHY preambles above it and so on. But okay, so here starts the IP. What we really care about was the source address, destination address for now. And after that comes a little bit of UDP header. And basically, it just says the source port, destination port, and it says how long the packet is. The checksum, we can ignore it for now. We couldn't actually we couldn't deliver anything to an application unless we had source port and destination port. We can deliver to the machine. With just the destination address, we know which machine to send it to, but we'll never know which application to send it to. So that's what the ports are for. Okay, TCP on the other hand, let's see if we have a TCP too. Oh. Yeah, looks a little more complicated. Source port, destination port again, sequence number, acknowledgement number. Those are the important ones, and the rest we can ignore for now. Okay, so UDP doesn't have a sequence number. It doesn't have any acknowledgements. So how does this all work out then? So now we're sending a packet. This is all for TCP. With UDP, bigger. There isn't really, there's no connection, because there's no connection establishment or anything. There's just a packet, and it says source port, source IP, source port, destination IP, destination port. All right? And that's all you get. There's no extra overhead, and there's also no extra support. So you can, as a client, you make a packet, you have it sent, and it just flies over to the other side, maybe. Sometimes it won't. Sometimes if you have two of them, they'll come in different order. If it arrives at the client, at the server, it'll certainly be delivered to the application. That's all there is to it, yeah.
Is the server supposed to send a feedback regarding I received it?
No, there's no acknowledgement. In fact, there's no way of identifying the UDP packet. They all look the same. If you send several packets with the same information in it, same source port and so on, they all look the same. So you don't even know if you got a duplicate.
So for most applications, you probably have to do some TCP first before you open UDP?
Nope.
It's either this or that.
Yeah, it's either this or that. Well, okay. So if you're doing say a voice call, then you really want to have reliability for the control information. You want to know, yes, I am connected to this guy. He's there. Right? They answered, stuff like that. And then you start doing the communication, the actual voice, and you'll do that with UDP. So oftentimes you'll have two. You have a little bit of UDP, a little bit of TCP, right? But certainly not all the time. Okay, there's one more thing that could happen. You could even get duplicates, and that actually happens for TCP as well. Sometimes the network reorders packets, or even copies of packets, and gives you two copies of it. Any idea how that might happen? Why would a network make copies? I mean, they're not stupid. They're not like, oh yeah, let's try to mess this up, right? That's not what's going on here. There's some mechanism that...
With TCP or with UDP?
The network. The TCP and UDP, they don't care. The network doesn't even know what they're dealing with.
Something might have guessed that the TTL should be constantly tried sending it to multiple rounds, and it ended up arriving anyway.
Wow, another very complicated scheme. Yeah. No, it's not. It's not that complicated. It's a very simple thing. Yeah.
The confirmation of receiving the packet get lost, so the client, I'm gonna send another one.
Exactly. Okay, so that's not even in the network. But so the server got the packet, sent the ACK, figures, okay, I'll deliver this to the application. I received it, everything is good. The client doesn't get the ACK. Now the client sends another copy. Right? That's what it's supposed to do. So this wasn't even the network doing it. It's just the client sending more copies. Okay, but the network something similar can happen in the network.
That case that we're just talking about wouldn't happen with UDP, or
No, it wouldn't happen with UDP. That's right. The network doesn't know about TCP. So it can't receive a TCP acknowledgement. I mean, it'll transmit it. It just doesn't know what's in there. So some links, like this wireless link here, is unreliable. Or that is, the radio channel itself is unreliable, notoriously unreliable. So it'll lose lots of my packets. The way they try to fix it is they have a link level retransmission. So when my laptop sends a packet, it goes to the access point within 10 microseconds, responds, yeah, I got it. Right? So that's only for this little link. If they don't respond within 10 microseconds, I transmit again. This is a whole different time scale than internet time scale, right? There we're talking milliseconds. So we're saving a lot of time here. Rather than losing the packet on the first link and then waiting for the server on the other end saying I didn't get it, now we're just dealing with it right here and sending again. Okay, so that's a massive improvement in terms of latency and also in terms of saving bandwidth and all this good stuff. But now we have the problem. The access point received it, sends the ACK back, the ACK doesn't make it to the laptop. And access point long since has transmitted the packet onward. Right? And now the laptop sends it again. Access point has no way of telling that this is the same, whether this was intentionally duplicated or if it's a retransmission. So it'll just send it again. So this happens on any link where you have retransmission for reliability. You're likely to end up with this problem as well. So duplication happens in the internet. It's not that common, but it happens. Okay, so let's. Those are all the things you have to deal with, and it's not nice. And UDP doesn't give you any performance boost. Right? You're not going to be able to, in principle, download something faster if you write it in UDP, because TCP is essentially written in UDP. It doesn't actually do that, but it essentially has the same exact conditions as UDP has. It just layers on some extra services which are extremely well written. Right? So we'll not be able to write something that's better than TCP unless we really spend some time on it. Right? That's many research careers have been spent trying to do it, and usually it doesn't end up working that well. So I would highly suggest not doing it. The only time when it makes sense, I keep pushing on this because people keep saying it in the finals. They say, okay, well, we want to do this faster, so let's use UDP, right? And it's just, okay. So, the only time when it makes sense is when you don't care if the packet gets there, but you really care if it gets there on time, right? That's when you want to use UDP. Let's do some UDP programming.
You're differentiating performance and latency, right? It's two different things.
Oh, yeah.
Okay.
So there's that's probably a core topic in 450 as well. But yes, we should talk about that. There's latency and there's throughput for a network. So you might be able to get one bit through get an answer very quickly, or get one bit to the other end with very short latency. But then if you wanted to give them a gigabit, it takes forever. See if I have a good example. Let's talk to Mars. All right, so I get this big, nice antenna, right? And on the other end, I have satellites, everything, like a whole array of satellites to receive it. Now I can do, maybe I have a laser, like these new free space laser things. So I can do hundreds of gigabits to Mars, right? And now I want to just tell them, good morning. How long is it going to take?
5 minutes.
Yeah, it depends. If Mars is on the right side of the sun and all this, it'll be about 5 minutes, maybe 8 minutes. If we're unlucky on the other end, it'll take about 30 minutes, no matter how fast the connection is. So that's latency. And then, let's see, do we have another example of... Yes, so if I have a serial cable, old school serial cable between my computer, of course it doesn't have a connector like that. No, we'll do just an audio communication between my laptop and your laptops. It just screeches a little bit, and your laptops pick it up. Whenever the computer screeches, you know that, it had something to say. Right? So we got a message across. How long is that going to take? How long to send, like, a 1 bit, the screech, from here to there? Come on. How fast does sound go? 300 meters per second. 340 meters per second. Okay, so this is about 3 meters here. So now it takes 10 milliseconds to get a screech from here to there. So sound is slow. Right? So we don't want to deal with sound. But still, 10 milliseconds isn't so bad compared to going to Mars. Now, sending a movie over from here to there is going to take forever. To Mars, it would take 5 minutes because we had short latency. So certainly the bandwidth is enormous. But the latency means we won't get acknowledgement that it actually got there. And they won't actually receive even the first bit of the movie any sooner than 5 minutes. And then 5 minutes and a half second after that, they have the whole movie. In this case, with the audio, the first bit of the movie gets across in about 10 milliseconds. And then we're going to have screeching for hours and hours, right? Because it's a really poor channel, especially with this thing over here making all this noise. So we have a really thin pipe, but it's very short here. And if we're going to Mars, we have an extremely long pipe, and it's fat like crazy, right? So oftentimes, to be honest, it tends to be like the short pipes are fatter and the long pipes are thinner, but it's not always like that. So that's why you tend to equate the two, I think.
So when you said that they always put on the final that performance of UDP is better than TCP, what do you mean when you say it's not? In that sense, you're saying it's not, or?
In no sense is UDP better performer than TCP. It has some different qualities. There's no way to say that it's better in general.
Okay.
And certainly for downloading a file, it's never better. It cannot possibly be better because TCP was made to be the best at downloading files. Right? So you write a very, very clever application on top of UDP, you can probably maybe get almost to TCP performance. You can get over that if you cheat. But that's not because things are going well, it's because you're screwing things up for everyone else. So, but that's certainly a CS450 topic, so let's drop it there. Okay, so let's send a few UDP packets. So we had I think we had a web client here. Let's make this a UDP client, UDP sender. So this is all the same. This is all the same. Let's send to a different port. And I want to send this to my... did Tim go through the get adder info in lab? Okay, good. So we won't do the get adder info here, but that would certainly be a good idea in this case. I think I remember the address of my web server. This is bits.cs.uic.edu. And so there's no connect, because UDP doesn't connect. We don't have a request, but maybe we have a message we want to send. Let's see. We'll go... I want to send a few different messages. So... like that. Okay, so now we have, now buff has a few different messages in it every time, and then we'll just send it. So let's look at this now. See any problems with this? I see a problem. CQC problem. It's right there. Oh, I'm sending rec. Okay, that's okay, good. It's not what I meant, but certainly that was a problem. Okay, no, there's something else. No. Oh. Okay. Everyone gets a little more time to think about the actual problem.
I'm still not perfectly certain how ASP.NET works, but it looks like we're...
Yeah, it works.
Oh,
It's fine.
this printf is like that. So you tell it where to write to, and then it's just like printf. It doesn't write it to standard out. It writes it into this character buffer instead.
The buffer's approximately 100 bytes.
Yeah, and how long is this? Does it look like 100?
No, I thought you're attaching
It's not
message I every single time, multiples of message I, right?
How would that work?
I don't know.
This here is a stack variable that only exists for this
Oh,
time.
right,
And even if it was out
yeah.
here,
Got it, yeah.
buff would not have been changed.
AFINet is that going to be allowing for UDP so TCP?
Oh, yeah, that's fine. That's just the internet family of addresses. That's fine. Yeah. No, there's a more principal problem here. There may still be a syntax problem, but there's something serious going on. It has to do something with that, yeah. I'm not telling it where to send it. Right? We used to have a connect. So now I just send. Alright, fine. So there's an address up here, but we're not telling anyone like that's where we want to send it to. So it's not going to work out. Fortunately, there's another one called send2 that lets us specify where we want to send it to. Okay. So for every message now, I get to send to a different address if I want. So it's very different from TCP in that sense. Yeah.
Something like if you, on the connection manual, you don't have to use send to. So if you're using just send,
Yeah.
you don't have to use the connection command. You have the connection second socket first.
Yeah, so in general, using send, you can do it with UDP. It turns out connect actually works with UDP, but it doesn't actually connect anything. It just remembers that this is the address you want. So I'm kind of skimming over that, but yeah. So if you have connected your socket, send2 makes no sense because you're only allowed to, at least with TCP, you're only allowed to talk to your endpoint, to the server that you connected to. With UDP, we don't care. So messages come in. It's actually the same thing here. If I have a socket and I've bound it to a port, I don't have to listen anymore. I just receive. If I'm a server, I just receive, and messages will come in as they please. All right, but we're a client now, so let's send these messages. I think we're good. By the way, I updated my OS last night, so let's see how things go. Ah, look. The warnings look all different.
Is it using? It looks very similar when you use the Clang compiler, right?
This is Clang, yeah. I thought for sure that they were using Clang for a long time, but it's...
Are you sure you downloaded the command line tools or whatever?
You had to.
Oh yeah.
seems to work.
Well, I had some weird errors when I updated the other day.
Yeah, I had to... Oh, yeah, you updated before yesterday?
He was on the previous.
Ooh. Okay. All right. Okay. Send. We need something more, right? We need a... So it doesn't care. It doesn't care if it got there. You know, I just send them right away and forget it. All right. We need to receive it somewhere. Let's go receive it. That should be the right machine. Oh, crap. Look at that. What's going on? I got logged in and it's looking for Wi-Fi. It's not plugged in. Wow. Okay, I think they have a few patches still. Okay, so as long as the connection works, I'm happy. All right, so let's make a server. So now I listen. On Linux, you have to say -p. I want that port, and then -u because I want to listen on the UDP port, not a TCP port. Actually, do we have that? No, we don't have that
Is it possible to
header anymore.
one port?
What's that?
Is it possible to divide it into one port?
No, they're completely different classes of ports. So if you look at the port numbers in those fields, it just says port numbers. So how can we tell if it's a UDP port or a TCP port? Well, it turns out in the IP header, there's a protocol field. So, and that says, okay, this is a UDP packet coming in. And now, whatever is inside there, now there happens to be port numbers in UDP packets. There wouldn't have to be. It could be port letters too if you wanted. Of course, UDP doesn't do it that way, but if you want to make your own transport layer protocol, you can use port names instead. Okay, so we're listening. And I had some weird things going on with Netcat on UDP, so I think it's going to quit on us after a little while, but it seems to not have quit yet. Send some messages. Okay, there they are. Did we get all of them? Looks like we got all of them. Let's see if we can. Let's see if we can not get all of them. Oh. Okay. Make it a little bigger. And we'll send 1,000 every time. So now we're using more bandwidth, and then we'll send a few more of them. So now we're saying a megabyte. Let's say, okay. How are we going to know if we got all of them? I was trying this in my office. I was trying sending some UDP packets in my office. I have really poor Wi-Fi there, so there it didn't work. Here, for some reason.
Can you route and seem to go to some text file and then
You can just check how many lines are.
Oh, check how many lines. Excellent. Yeah, we can try that. Ding. Okay, send. How do we know if this one's done? All right, there was some delay at least. Okay. Oh, yeah. So I sent 10,000 and I got 1,700. It's a pretty good score. What? Oh. Okay, there. So the reason it looked like crap like that is I sent this whole buff of 1,000 characters, right? And a lot of it was uninitialized. So, but now I just pulled out whatever looks like strings, and so now, see, in the beginning maybe we got all of them, yeah. But at some point, the buffers start getting exhausted. So on my laptop, probably the operating system has quite a bit of room to store outgoing messages, but then the network connection is just not fast enough, so it's gonna at some point start having to throw away some packets. Where are they?
throw out a lot?
Yeah.
I don't see any response.
It skips by 40.
Oh, I see. It skipped a lot, and then it caught up, and
Oh, wow.
yeah, at the end there, it got a little tired. Yeah. Okay.
Just takes whatever it fits.
Well, so it looks like they were in order here.
Yeah.
So that's something. I tried it on my LAN in my office, my Ethernet connection, and there everything arrived out of order, like completely randomly out of order. I have no idea why that happened. So anyway, we can send really fast. Try that one more time. I'm sending, so that was 10 megabytes, right? Just like that. Pretty good. Unfortunately, that doesn't mean they received at that rate, right? They got at some other rate. So that's UDP. Okay, so yeah, we're not going to move on to multi-threading now. More questions on UDP, on TCP, connections, anything?
You have to specify if the port that you're connecting to is from TCP or UDP.
Mm-hmm.
So that means like you have one port, then does it just matter when you set up like server whether you just specify that port as your TCP, or is it like specifically that port has to be used?
So they are completely separate domains. They happen to look the same. So port 8000 is the same number for UDP and TCP, but they have nothing to do with each other. If we look at the code here, we had here the sock dgram. That's what specifies that this is a UDP socket. So that's before we select a port or anything. And then it so happens that they both use 16-bit port numbers, but it really could have been anything else. Oh, yes, the web proxy, the homework. Let's see, what was it I was going to tell you about?
The last part,
Yeah. Right. So that's all fine. The difficulty that I had, which I don't expect you to resolve unless you want to, is if you try to open a website with a browser using this proxy, it's going to be a bit of a problem, because the browsers have strict expectations on standards compliance on the proxy, and it wasn't as easy as I first thought to get that right. So the main thing is the browser is going to make one connection to your proxy, or maybe 5 or maybe 10, but it's not going to make unlimited number. It'll make one, let's say, and then it'll ask the proxy through that connection for all sorts of different documents, HTTP documents from different servers. So there isn't a one-to-one mapping between the incoming connection from the client or from the browser and whatever you make to the server. Now you have to read through the request from the client and say, oh yeah, it's for that server. Oh, and here comes another request, and that's for that server. Right, so there's a lot of string parsing, which didn't seem like quite the topic of this homework. But let's see. Did Tim show you with NC how a web proxy works? No. Okay. So we'll just do that very quickly. The web proxy is super simple in its basic form, and when we use it with wget, which just fetches a single HTTP document, it remains that simple. So we'll stick with that. HTTP proxy. So now I'm just configuring wget. It looks for this variable. I'm configuring it to use my my local machine port 1234 as the proxy. Okay. So now I start listening to port 1234. So that's my pretend proxy over here. And now let's see. Let's do a wget. Google.com. So now I'm trying to fetch something from Google, but it's not going to connect to Google. Usually it would connect to the host name in there. Now it's going to connect to my HTTP proxy, and then it's up to the proxy to do the work. So there's the request. Now it's waiting for the response. So I can say HTTP 1.1, 200, OK. That's the header. And then see. Okay, so there, now it's finished, and now we can see. What? Oh, index.2. Right? Okay, so that's all a web proxy does. So what you need to do is just read this stuff, connect to the right server, cut off the file name and that sort of thing, go fetch the data, and then there was a little bit of extra stuff, like in this case, the user agent, you're supposed to change that, put the 361 in there, and if there are any cookie headers, and those are not going to show up with wget, because wget doesn't do cookies.
What about the port? We didn't need that.
The port. Right, which port? What? So I told it here to talk to a proxy at that port. HTTP is always port 80. Almost port 80. Almost always. I wanted to do just this very simple one more thing. Firefox. Firefox is the only one I managed on OS X to configure to use a proxy, because there was something broken with my settings. Here, I'll tell it 1, 2, 3, 4. So now it's configured. Then we go to google.com, and now we're listening over here. Here it is. Okay, we got some sort of request. This was something before, apparently. You know, they do all this other stuff. Now it's looking for, like, is this a, I don't know what it's doing. Anyway, so I got a request. I can send a response. Okay, didn't work. It wasn't expecting a document. It was expecting some other safe browsing whatever stuff. And now I closed the proxy, so that didn't work out. Anyway, let's wrap up, and I'll see you Friday.
The thing I was talking about with the command line looking different, GCC. If I type GCC and compile something on here, it looks like the old way. But if I type plain and then compile it, it looks like the new way.
Do you have the new OS?
No, the old OS.
Ah.
That's